Okay, hello. So in this video, we'll review some concepts from multivariable calculus, but in this case, we'll focus on integration. How do we deal with multiple integrals? How do we integrate over regions that are not one-dimensional, etc. And so here we can see the topics. So first, we'll remind or kind of review what iterated integrals are. Afterwards, we'll talk about what integrals over regions in the plane. How do we make sense of those? We'll talk about line integrals, which are one-dimensional integrals, but now they come from kind of curves in higher dimensional spaces. And then finally, we'll talk about surface integrals. Okay, so what are iterated integrals? If we have an expression of the form that, right, where we have one integral out here, one integral in here, and then this inner integral is with respect to dx, this outer integral is with respect to dy, and we're integrating a function of two variables, x and y. Question is, how do we make sense of this? How do we compute this? Well, what we do is first, we compute kind of this first inner integral. And so this inner integral, right, notice that we're integrating a function of x and y, sure, but here y is going to be fixed, okay? So y we'll treat as a constant. We'll integrate this function with respect to x between the bounds c and d. We're going to get some function of y, right, because we've integrated out x. And then what we do is integrate kind of the outer integral, which, right, this we're integrating with respect to y, we're integrating from a to b, say. But once we've done this integral in here, now we have a function of y, because we've integrated out x. And then what we do out here is we integrate out y. And so in the end, we should end up with a number, a scalar. Okay. So as an example, question is, what is the integral of y times e to the xy? Okay. Integrating with respect to dx and dy. Well, so in here, right, this is saying integrate with respect to dx, okay, and keep y fixed. Okay. So if we do that, we're going to end up with something like this, right, where we have, so the integral of constant times e to the x times the same constant. The integral of this function right here is exactly e to the xy. And we can double check by differentiating this with respect to x, right? Because we integrated with respect to x, and we end up with exactly that, this expression, okay? So we integrate with respect to x, and then we evaluate the bounds. So that's what's happening there, okay? What does that give us? It gives us this difference, right? But here, right, kind of this evaluation doesn't do anything with y, right? It only tells us how to evaluate x. So y is still a variable, okay? So here for the second integral, now we're integrating with respect to y. Okay. So what does that look like? Well, we get something like this, right? If you integrate this with respect to y, you're going to get that. Integrate this with respect to y, you're going to get that. And then we evaluate the integral or the antiderivative of this between these two bounds, okay? And we're going to get something like that, okay? But the takeaway is, right, whenever you have an iterated integral, just start with the innermost integral, compute that integral, and then work your way out. Okay, so, you know, it's all well and good. But in practice, what happens is we don't necessarily define or state these. We don't set up the integrals we care about as iterated integrals from the get-go. Okay? And so an example of this might be an integral over kind of a planar region. And so our setup for this will be kind of our region R is going to be the set of X and Y such that X is between kind of this above A and below a value B, and Y is above a value C and below a value D. Okay. What does that look like? Well, we can sketch a picture like this, right? So if you pick a point here, right, this is going to be the point X comma Y. Question is, what's the X coordinate? Well, it can be anything between A and B, right? Similarly for the Y coordinate, anything between C and D. Now, this is a very simple planar region. Usually we'll be working with more complicated regions, but this is just the starting point. Okay. Okay, so we're given a region, and we're also probably given a function defined over that region. Okay, so a natural question is, well, how do we make sense of the integral over that region of our function? Okay. And so I've written dx dy here. Usually you'll see this as dA or some other kind of area element or volume element or something like that. But the question remains the same, right? How do we integrate this function defined by two variables over this two-dimensional region? And so in practice, what we do is, well, we evaluate this iterated integral. Okay, so right, kind of what is the area under the surface given by this function over the region R? Well, it turns out that that's going to be exactly the iterated integral where first you integrate out X between these two bounds, and then you integrate out Y between these two bounds. Okay, so in practice, integrals over arbitrary regions, how do we actually get a value for those integrals? We compute these iterated integrals. Okay. So this example was given in kind of Euclidean coordinates, right? The X coordinate was between two values. The Y coordinate was between two values. And so kind of a natural question is, well, what if we change the coordinate system, right? So instead of Euclidean coordinates, what if we use polar coordinates? So for this setup, what we're going to do is we're going to say, well, the region we care about now is still going to be a rectangle, okay? But it's going to be a polar rectangle, okay? So for polar coordinates, we're looking at a value for radius and a value for angle. And the prescription is the radius is going to be between A and B, and the angle is going to be between C and D. Okay. So what does a sketch of this region look like? Well, something like this, right? Where we say, okay, pick a point here, right? This is going to be, so a point there is going to be r comma theta, where the distance to the origin is r, and then the angle kind of this vector makes with the x-axis, that angle is going to be theta. Okay. So what we're doing is we're saying, well, we want all points whose distance to the origin, r, is between A and B. Okay, so that's kind of our lower and upper bound. We're also saying that we want the points whose angle, right, that vector makes with the x-axis is between C, which is the lower bound, and D, which is an upper bound. Okay, so we're saying, right, all the points who are at least A units away, but no more than B units away, and whose angle is no more than d radians, but at least c radians, okay? So the region bounded by all of these, as prescribed, is going to be this thing in here, okay? So that's where we get the sketch of R. Okay. So what does an integral look like with respect to polar coordinates? It would be nice if we could just replace dx with dr and dy with d theta. But in this case, we can't quite do that. And so the correct sort of substitution is going to be this. So instead of dx dy, which is this infinitesimal kind of square in Euclidean coordinates, the corresponding infinitesimal square is going to be r dr d theta. Okay, and so then, right, our function, if instead of expressing it in terms of x and y, now we're expressing it in terms of r and theta. Okay, and then we're integrating this function with respect to r dr d theta. But otherwise, we're computing these iterated integrals still. Okay. So why r dr d theta? And why not just like dr d theta? Well, one way to kind of think of this is, right, if we take this infinitesimal kind of square dx dy, right, question is what units does it have? Okay, so dx is going to be an increment in the x direction. This is going to have units meters or length. dy is going to be a tiny step in the y direction, okay? But this is also going to have units meters or length, okay? So if we take meters times meters, then we end up with units of area or meters squared. Okay, so if we compare that then to the polar coordinates, right? The variable r that we were using, right, that's measuring length. That has units meters. Okay, so dr is the right sort of thing to use. Okay. But this variable theta, turns out theta is actually unitless. Okay. Maybe one way to kind of see that is, well, ask what is the arc length of a circular segment, right? Say you have a circle, okay? Actually, I think I have a picture. Yeah. So fix a circle of some radius a, okay? And then say we want the arc length, we want the arc length for the arc that's starting at angle 0 and going up until angle C. Okay. So as a picture of that, we're going to have something like this, right? Where kind of, right, this is the angle of this segment. And then this is the distance to the origin of the circle, or the radius of the circle. Okay, so the question is, what is the length of this arc right here? And so it turns out the arc length is going to be, well, whatever angle we're picking up times the radius of the circle, okay, which in this case is c, which was the angle, right, times a, which is the radius. Okay. So arc length, right, measure of length, this has units meters. Radius has units meters or length as well, which tells us that angle is unitless. Okay. Okay, so then what that gives us is this object right here, RD theta, right? This is going to have units length, which matches, right, kind of the setup from before where we wanted length times length. dr has length. RD theta has length. And so in this case, RD theta is going to have units length squared or area. Another way to kind of intuit this is, right, RD theta, okay? D theta is going to be this infinitesimal angle measure. And RD theta is going to be the length of an infinitesimal segment, right? So if we go back up here, so if this angle difference is small, right, the length of this arc is going to be approximately A times D theta, where the length of this arc is going to be approximately B times D theta. So if this width is really small, meaning A and B are really close, then the area of this square is going to be approximately, right, this kind of difference in radii, or dr, times the width of this square, which is going to be approximately RD theta. So then the area of this is going to be approximately RD theta times dr. Okay. Yeah. So RDR d theta will have units area or meters squared or length squared, which is what we want if we want to measure kind of these area units. Okay. So another kind of integration technique is this approach using line integrals. Okay. So in one dimension, right, if we say, well, we want to integrate a function of a single variable x, right, what we're doing is we're kind of taking one way to construct this integral or to compute this area is take this small increment delta x, kind of approximate the height of this rectangle by some function value. And so then the area of this rectangle is going to be approximately this length times the function value. Okay. And if you add them all up, you end up with the area under this curve. Okay. So in 2 or higher dimensions, we can do a similar thing. Okay. We can ask, what is kind of the integral of a function along this one-dimensional object, like a curve in the plane? And the setup in this case is going to be the following. Okay, so gamma down here, this is going to be our one-dimensional curve. This is going to play the role of, say, the x-axis right here. Okay. Now, if we and so here we have a function of 2 variables, kind of indicated by the surface. Okay. So what we can do is for each point along this curve, we can ask, well, what is the value of this function at each of these points? Okay. And so that's what this blue curve here represents. Okay. And so then the question might be, well, what is the area under this kind of function curve, right? Where the area we care about is kind of what I'm coloring in as this curtain. I have a picture of that in a second, but right, so just so it's written down. So this path gamma, right? We can represent that as kind of a function where you plug in a number or plug in time or whatever other parameter, and you get back 2 numbers. First one is going to be the x coordinate, right? What the x coordinate is for your path. The other one is going to be what the y coordinate is for the path. Okay, so that's the path gamma. And then, as I said, the blue curve is the function we're interested in, f, evaluated at points of the curve. And so another way to write that is f of gamma 1 of t, comma, gamma 2 of t. And so the question I was getting at, well, what is this one-dimensional integral, right, with respect to this one-dimensional curve for this two-dimensional function or higher dimensional function? Okay. Cool. So what we would like to do is set it up as an iterated integral, because that's how we actually compute multiple integrals. And so how we're going to go about this is we're going to say, okay, well, if the path gamma, say it starts at t0, right? Start the clock, you're standing somewhere. As the clock runs, you're walking around the plane, and the path you follow is described by gamma. Okay? Walk around for a bit. At time L, you stop. Okay. So another way to kind of write this thing is say, well, we're walking along the gamma curve, or the curve gamma, and that's equivalent to integrating, or starting at time 0, figuring out what point gamma you're at then, and then ending up at time L and seeing what point gamma you're at then. Okay. So that's what this first kind of substitution is. Instead of integrating over gamma, we're now integrating from 0 to L. What points are you plugging in? Well, we're plugging in points along the curve gamma of t, where t starts at 0 and goes to L. Okay. So this is a function of one variable. This is an integral for one variable. The only thing we need to worry about now, though, is this ds, right? This is going to be a line element, or kind of a measure of arc length for your curve. And so what we need to do is express this in terms of t and dt. And so that's what we're going to do next. And so the picture I drew before, kind of with the curtain, trying to find the area under this curve, is replicated sort of here, where now what we're interested in is the area of this orange curtain. So in one-dimensional integration, right, where we had a function f of x, as we were walking along the x-axis, right, kind of the tangent, or the arc length for that curve was just this dx, right, delta x, just however large of a step size we took. So in the higher dimensional version, we need to be a little careful, because, right, we could step in the x direction, we could step in the y direction, or we could step in some combination of both. Okay. And so especially when we have that combination of an x and a y piece, that's where ds tells us the correct kind of arc length to measure. Okay. So in 1D, as I was saying, right, this is a function, close enough. This is a function y is equal to f of x. And so then for a tiny interval delta x, we look up and we see here's kind of the change in y, right? And so if we zoom in, right, well, for a tiny step in x, and this should read delta y, so if we take a tiny step in x, right, what is the corresponding change in y? Well, we're going to have these two values. Okay, but notice that this curve isn't just, right, horizontal or vertical, right? It has kind of it makes an angle. Okay, and so if we want to figure out what the length of this little piece right here is, right, well, we need to, essentially what we're going to do is use Pythagorean's theorem and say, well, the length of this tiny segment is going to be the square root of this length squared plus this length squared. Okay. So this arc length piece, right, the kind of the infinitesimal length of the curve, is approximately this little step in the x squared plus a little step in the y squared. And so I've written everything with squares, but if you take the square root, you're going to end up with something like this. As you take the limit as delta x and delta y go to 0. Okay, so the observation here is, though, right, the kind of points x and y that we were taking, these depended on some parameter t, right? So technically these were like gamma 1 of t and gamma 2 of t, where gamma 1 was the x coordinate, gamma 2 was the y coordinate. Okay, so as we step along this path, as t increases, we need to figure out what kind of this arc length is with respect to kind of maybe how fast we're walking, right? What this parameter t is. And so that's kind of the motivation behind computing this thing, right? But we can get at this in a kind of naive way where we say, well, ds is this term, sure. So if we divide this thing by dt, we end up with this thing right here, sure. Now what we're going to do is move this thing inside. Okay, and so the key point here is that, well, here we get a dt squared, right? Because if you take this, move it out, you're going to have a square root of, right, the thing that you pulled out. So the square root of this thing is just 1 over dt, which is what we have there. So these are equivalent. Okay. Now, if we distribute this to the other terms, we're going to end up with this piece right here. Okay. So what this tells us is that this arc length, how this arc length is changing with respect to time, is the square root of how our x coordinate is changing with respect to time squared, plus how our y coordinate is changing with respect to time, quantity squared. Okay. And so when we have an actual curve gamma, where the x coordinate is gamma 1, the y coordinate is gamma 2, this kind of ds dt takes this form, right? Where we're computing how, again, our x coordinate is changing with respect to time and how our y coordinate is changing with respect to time. And now if we take this dt that we introduced to kind of help with the computation, take this, multiply it on both sides, we end up with this arc length element, right? How we're measuring kind of the base of this rectangle for this, possibly wonky curve. This arc length element is going to take this form. Okay. So putting all the pieces together, right? This integral right here, we converted to integral from 0 to L. This function right here, we were evaluating at gamma of t. Okay. And so now with, right, this arc length or line element, right, we have this expression right there. So altogether, right, writing out this integral, this line integral, in practice, how do we compute it? Well, it's an ordinary integral, right? How we usually can kind of evaluate these. It's just for a one-dimensional integral. It's just we need to be a little careful with how these pieces come into play. But in the end, we've converted this expression to an integral involving t between 0 and L. And presumably this will be something we can actually evaluate. This is something we can actually compute. So this whole thing will be something we can compute. Okay. So long story short, we take this right line integral here, this expression, and we convert it back to kind of an iterated integral or just one iteration. But yeah. Okay. And so the last kind of topic that I wanted to mention in these notes are these surface integrals. Okay. So the question is, if we write something like this, okay, so similar to the line integral, but now R is going to be kind of a piece on a surface. ds is going to be like an area element, but on the surface, right? So especially if the surface is curved in whatever which ways, this may not have as nice a parameterization as just like a square in the plane. This might not have as nice a representation as just like dx dy. Okay. And so the question is, how do we make sense of these kinds of expressions? So in practice, if we have something like this, we want to compute it or transform it in a way so that we can compute an iterated integral, where du and dv are some kind of like length elements, or similar to like dx and dy. And so then this is going to give something like an area. And so I say we compute something like this, but there are going to be some other pieces we may need to incorporate, okay? Because as written, this doesn't necessarily take into account the geometry of the region R. Okay? So the question is, how do we incorporate that geometry? Okay? So R is going to be some surface, and ds is going to be some small like area measure on that surface. Okay. So here's an illustration. R is going to be a surface like this. Okay. And so if we zoom in somewhere on the surface and look at a tiny little rectangle, right? The rectangle may look a little curved, but this is going to be kind of our starting point for all of this, right? So we want to integrate over the surface. We want to take all of these small area patches, evaluate our function over all of these little patches, and then add them up. Okay. And so then that would be what this integral is kind of in spoken word. So first things first, we need to parameterize our surface in some way. Usually how we do that is we pick some other coordinate system, say uv, and we say, give us parameter u, give us a parameter v, and we will tell you what point in 3 dimensions corresponds to that choice of parameters. So what are some examples of this? Well, we want to look at a sphere, right? Surface of a sphere, let's say radius 1. One way we can parameterize that is by taking the coordinates uv and map those to sine u cosine v, sine u sine v times cosine u. Okay, so oftentimes u and v will be written something like theta or rho, but these give you 2 angles telling you kind of where you are on the surface of the sphere. And what are the possible values for u and v? Well, u is going to be between 0 and pi. Usually u will be kind of, if you look straight up, that's going to be u is equal to 0. As you start looking down, u is going to increase until you get to pi, which you're looking straight down. And then v, as I've written here, is kind of the angle you make as you sweep around the circle or the sphere like this. Okay. So that's just one example of a parametrization. Another example would be something like this. Take this kind of parabolic sort of bowl. What's the parametrization? Well, plug in two parameters u, v. What are your three-dimensional coordinates? First coordinate is just u. Second coordinate is just v. Third coordinate is going to be u squared plus v squared. And so for this x, y, and z coordinate, or a z is equal to x squared plus y squared, you're going to get something that looks like this. Okay. So what's the utility of a parametrization? It lets us convert an expression like this to something kind of like this, where now we're evaluating our function at certain parameter values, and we have this iterated integral. Okay. But the remaining question is what the surface area element is, right? How we're measuring area on the surface of kind of the space that we care about. Okay. So what is ds? So one way we can kind of draw this is say, well, right, so going back up here, we had this picture, right, where we had this tiny ds. So where do we come up with this? Well, right, what we can do is say, okay, so in our coordinate system, let's fix one of the parameters a, or so fix one of the parameters, say u to be equal to a, right? And so as we vary the second parameter v between, say, v is equal to c and v is equal to d, we might get something like this. Okay. So if we were to evaluate, I'm going to say this. So the curve a comma v, where v can vary, right? So we fix the first parameter, so set u equal to a and then let v vary. That's going to give us a curve that looks something like this. And then we're saying, well, we just want v kind of in this range. If we fix the same parameter u, but now we change its value, so now instead of u equals a, we're looking at u equals b, that's going to give us maybe a curve that looks something like this. Okay, so this is the u is equal to b curve, u is equal to a curve. This is the v is equal to c curve, and the v is equal to d curve. Okay, that's just how we can kind of parameterize this stuff. But what we're doing is we're saying, okay, well, fix one of these coordinates, vary the other one. So u is equal to a, vary v. This is going to be, so this point right here is u is equal to a, v is equal to d. Now we can fix v equal to d. We can vary u to go up there. This is u is equal to b, v is equal to d. And now we can vary v again to kind of go there. And then now we can vary u to get back there. So this little square we get by varying each of these parameters kind of at once. And what we want to do is say, well, if the change in u is really small, so if this is really small, this length, and if this length is really small, then that's going to be approximately our area element. Okay. So what is the area of this thing? Right, well, from this picture, it's going to be the length of this times the length of that. So in practice, it's going to be kind of approximately the area of this parallelogram. Okay. So if this distance is small enough and this distance is small enough, we'd expect that this curved piece right here and this curved piece right here, those are going to be approximately, say, straight lines. And I've exaggerated the vectors, but this is going to be approximately straight. This is going to be approximately straight. And so then the area of this whole thing is going to be approximately the length or the area of this parallelogram. Okay. So then the question is, well, how do we compute kind of this parallelogram? This vector right here is what we get if we fix u is equal to a and then we take the derivative of this function with respect to the second coordinate, v. Okay? Likewise here, fix v, take the derivative in u, and we're going to get this tangent vector. They're going to form a little sides of a parallelogram, take that area. That's going to be our area element ds. Okay. So that's what I've written there. What are these partial derivatives? Right? How is u or f changing with respect to u? Well, let's look at how each of the coordinates are changing with respect to u. Likewise, how is f changing with respect to v? Let's look at each of the coordinates, how they change with respect to v. So in the end, we're going to get something like this. So this line element ds is going to be approximately at the area of this parallelogram, which we can compute via this determinant, right? So this is maybe a general formula for the area of a parallelogram, where you take the vectors that make up the sides of the parallelogram, compute the normal vector, or like the cross product of those two vectors, say, right, vector 1, vector 2, their cross product is going to be kind of the thumb that points straight up, right hand rule. So this area element is going to be approximately the length of the normal vector, and the normal vector we can compute via this determinant. And so if you go through a bunch of steps, eventually you're going to end up with this is an expression for the normal vector. Right? And so then the norm of this is going to be this expression here, just the square root of the squares of the coordinates of your vector. Okay. So this whole thing tells you the area of kind of an infinitesimal surface area piece. Okay. So this formula looks messy. In practice, you'll actually compute these derivatives. Things will cancel, will be much nicer. But yeah. So one way to maybe write this is, right, the surface area element is going to be the norm of kind of this normal that we're computing with these partial derivatives times a little area element in kind of the parameter plane or the parameter space. Okay. So bringing that all together, what do we get? Well, this whole integral becomes, right, so the integral of a function over a surface becomes this iterated integral of our function with respect to how we parameterize the surface times the surface element. Okay. Yeah, you can do similar things in higher dimensions, right? Just add a few more integrals there. But hopefully this is enough of a refresher for how we integrate in kind of more than one dimension.